this video, we'll talk about one application of Thevenin's theorem, and that is the maximum power transfer. Let us say that we have a scenario where a variable resistance is connected to a linear two-terminal circuit. So a variable resistance is that resistance that we can change its value. I've redrawn that circuit here, where the linear two-terminal is drawn as a Thevenin's equivalent. Now, take note that R here is getting power from the linear two-terminal circuit, and that power varies depending on the value of the resistance. So the question now is, what would be the value of the resistance in which it absorbs maximum power from the two-terminal circuit? Without any proof, let me just state that for R to absorb maximum power, its value must be equals to RTH, where RTH is the Thevenin's equivalent resistance that we will get if we convert that linear two-terminal circuit into its Thevenin's equivalent. I have a separate video, an optional video, where it is shown how this relationship was derived, so you can view that material after this video. Let us work on this example to illustrate maximum power. Here we are required to determine R sub L that would absorb maximum power. After determining R sub L, we're then required also to compute for the power that is absorbed. In order to accomplish this, we need to convert this part here into its Thevenin's equivalent and come up with a simplified circuit that looks like this one. To compute for VTH, we use this circuit and determine the voltage across these terminals. So this is our VOC, where this is plus and this is minus. To get VOC, we need to simplify the circuit. Now we notice that this part here is a current source in parallel with the resistance, and likewise for this. So we can use source transformation to simplify the circuit. For the 4 amperes and 2 ohms, so we have a voltage source that is in series with the resistance. This is 2 ohms, and the voltage is 4 times 2, so 8 volts. Okay, so this is our 4 ohms here. Okay, so this is 4 ohms. And the other pair, 2 amperes and 6 ohms, we can draw that as a voltage source also with a plus here. And this is our resistance, where this is 6 ohms. And the voltage is 12 volts. Okay, so this is our 20 volts here. So this is plus minus, and this is A here and B here. So this is our VOC, and this is 20 volts. Notice that this is an open circuit, and therefore there is no current in this loop. Okay, so current here is 0, but we can still write KVL. So doing that, that would give us this one. So starting here, let's start here. So that would be positive VOC minus 20 minus the drop at the 2 ohms, but there's no current, therefore that is 0. So we could ignore that. So minus 8 minus 12 equals 0. And that should give us VOC equals 40 volts, which is also our VTH. To get RTH, we can use this circuit, which is the same circuit that we used to find VTH, only the independent sources are disabled. So here it is very clear that RTH is equals to the sum of the resistances, which is 12 ohms. So now that we have RTH and VTH, we go back to our Thevenin's equivalent where RL is connected, and from this, if we want RL to absorb maximum power, this value here should be equals to 12 ohms, so the same value as this one. And now that we have RL, the question now is what is the power absorbed by RL at a value of 12 ohms. So we could either get the voltage across RL, so let's call it VL, or the current through RL. If we get the voltage, uh, so we can get the voltage using voltage divider. So this is 40 volts times a factor, which is 12. So this is 12 here, plus the total resistance, and that should give us VL equals 20 volts. We can get PL using V squared over R. So that is 20 squared divided by 12. And that should give us 33.33 watts. Okay, so this is our answer. And of course, this one. Okay, where this is our RL. For this example, we're just asked to determine what is R sub L for maximum power transfer. To do this, we again determine the Thevenin's equivalent of this one in order to come up with the circuit. Take note that we're only asked for R sub L, so that means that all we need to do is find RTH. We don't need to really find VTH. To get RTH, um, since the circuit contains a dependent current source, we would expect that case 1 cannot be used in finding RTH. So we are left with case 2 and case 3. But here, let me use case 3. Okay, so in order to use case 3, we need to find VTH as well as I sub n. So for I sub n, or VTH, we need to find the open circuit voltage of this open terminals. So let's say this is our A and this is our B. Okay. Take note that VOC is also the voltage across the 3 ohms. So if I can find this voltage here, that will be VOC. To get the voltage, I need to know the current here. Now, since the circuit is open here, that means that this current 10Ix will simply flow directly to the 3 ohms. So that means this is also 10Ix. Okay. So therefore, I can say that VOC is equals to the voltage across the 3 ohms, which is 3 times the current, which is 10 Ix, and that should give me 30 I sub x. So, but what is I sub x? Well, I can um, write a KCL on this node. So take note, this current source is dependent on the current that flows in this branch here. So doing the KCL on this node, uh, so that will give us current entering, so that is I sub x plus 0.9 minus 10 I sub x equals 0. So that means that we have here I sub x equals 0.9 divided by 9, or that is equals to 0.1 ampere. Now that we have I sub x, we can compute for VOC, and that would be equals to 30 times 0.1, or that is equals to 3 volts, which is also our VTH. Next, we find I sub n. So to get I sub n, we apply a short between terminals A and B and find the current that flows through the short circuit. So we call it I sub SC. Now, if we apply a short across AB, um, we can ignore the 3 ohms because the current that flows through here would be a 0, or there is no voltage um, through that resistance. So we could ignore this in the circuit. So that means that the current that is flowing here would be equals to 10 I sub x. Again, we apply KCL here. So we'll get this same equation. That means I sub x is again equals to 0.1 amperes. And that should give us ISC equals to 10 times 0.1, or equals to 1 ampere, which is also our I sub n. Now I can compute for RTH, and that should be equals to VTH over I sub n, which is 3 divided by 1, or equals to 3 ohms. So therefore, my R sub L is equals to RTH, which is equals to 3 ohms. And this is my final answer. Thank you.